Welcome to the deep dive. Today we're looking into something pretty critical in aerospace, keeping those composite structures sound, especially when they get hit by, well, unexpected things.
Right, like maybe a dropped tool on the tarmac or even runaway debris. Small impacts, but potentially big consequences for these lightweight materials.
Exactly. And increasingly, the way we monitor this involves smart sensors. It's actually amazing how much research is pouring into fiber optic sensors, FOS, for aircraft now.
It really is. And one really interesting structural approach is the pro-bionic lattice shell, PBLS for short.
PBLS. Okay, what makes that special?
Well, instead of just layers, picture three systems working together. You've got strong load-bearing ribs, then these protective tabs designed to take the hit, and an outer elastic skin.
Ah, so the tabs and skin act like a shield for the important ribs underneath.
That's the core idea, yeah. Protect the critical load-bearing parts from direct impact.
Okay, clever. But protection doesn't mean invincible, right? If something does hit it hard enough, how do we even know? Especially the severity. You mentioned traditional inspection is tough here.
That's the crux of it. The complex, integrated design makes standard non-destructive testing methods, well, let's say challenging to apply effectively.
Which brings us right to our main question for this deep dive. Can we actually use fiber optic sensors, maybe bedded right inside those protective tabs, to figure out where an impact happened and how hard it was?
Precisely the question researchers are tackling. Embedding FOS in those thermoplastic tabs seems promising. And to figure out if it works and how well, they started with numerical modeling.
So computer simulations, running virtual impact tests.
Exactly. Powerful simulations to see how the whole structure, including the sensors, behaves under different impact forces. It gives you a good initial picture.
Okay, so what did the simulations suggest? Where's the sweet spot to put these sensors for the best data?
The modeling pointed pretty clearly to the upper part of the tab, right up where it meets the outer skin.
Okay, near the surface then. Why there?
Because placing them there lets the sensors effectively record the residual strain after an impact. Think of it as the material remembering being stretched or compressed.
Residual strain. Got it. Like a lingering effect.
Yeah. And for a fairly hefty impact, say 50 joules, the simulations showed the sensor might see a peak strain around 2%, but crucially, it leaves behind a residual strain of about 0.5%.
And 0.5% is something we can reliably detect with these sensors.
Oh yes, definitely within their capabilities, a clear signal.
So if we can detect it, can we tell the difference between like a minor bump and a really serious hit?
That's the really useful part. The research found a clear link, a monotonic relationship actually between the impact energy and that residual strain. Meaning as the impact energy goes down, say from that 50 joules, maybe down to just 5 joules, the residual strain recorded by the sensor also goes down consistently from around 2%, sorry, the peak was 2%, the residual from 0.5% down to maybe 0.057% or so for 5J. Wait, let me check my notes. Ah, yes, the residual strain decreases from about 0.5% at 50J down to lower levels at lower energies. There's a typo in the original notes here. The original research actually states 2.07% peak strain at 50J, 0.5% residual, decreasing to 0.57% peak strain at 5J, with a correspondingly lower residual. The key is the monotonic decrease in residual strain.
Okay, ignore the exact numbers for a sec. The main point is higher impact energy leaves more residual strain.
Exactly. So reading that residual strain gives you a pretty good estimate of how hard the structure was actually hit.
That's powerful. But even with the tabs taking the brunt, I guess a big enough impact, like that 50 joule one, could still damage the main ribs underneath, the carbon fiber parts.
That's a definite concern. The simulations did show that at 50 joules, you could potentially see damage in the CFRP ribs, things like compression along the fibers or tension building up across them.
Which could lead to cracks, eventually.
Potentially, yes. That's the risk you want to avoid.
So is there a way to beef up that protection for the ribs without adding loads of weight or making it super complicated?
Well, the researchers looked into a rather neat modification, adding a very thin layer, just 0.5 millimeter of aramid fabric reinforced plastic, AFRP. Think Kevlar-like material.
Where does that go?
Right underneath the thermoplastic tab. You'd maybe make the tab slightly thinner, say 4 millimeters instead of 5, to accommodate it.
And this thin aramid layer makes a difference.
It seems to. The simulations showed it really helps restrain the sideways stretching the transverse strain in the tab itself when it gets hit.
And by controlling that sideways stretch.
It significantly reduces the stress concentration on the CFRP rib below, making it much less likely to crack. And crucially, this modification didn't really mess with the skin strain or the FOS readings much.
Ah, so you get better rib protection without losing your impact detection capability. That sounds like a win-win.
It's a pretty elegant solution, yeah.
Okay, so if you're actually building this into a plane, what kind of fiber optic sensor technology is best suited? You mentioned FOS, but are there different types?
There are. The main distinction here is between point sensors like fiber Bragg gratings or FBGs and distributed sensors like Brillouin or Rayleigh scattering-based systems.
And the difference.
FBG sensors measure strain only at specific predefined points along the fiber. Distributed sensors, on the other hand, can measure strain continuously all along the fiber's length,
Right, so if you don't know exactly where an impact might occur,
which you usually don't on a large structure,
right,
then distributed sensing is the way to go. It lets you pinpoint an impact anywhere the fiber runs within that PBLS structure. FBGs might miss it if it happens between grating points.
makes sense. Distributed gives you the full picture. This has been really insightful looking at how we can make these advanced structures not just strong, but also smart about their own health.
It's fascinating stuff. The level of detail these sensors can potentially provide about what's happened to the structure is quite remarkable.
It really is. So maybe a final thought for our listeners to chew on.
Sure. Given how sensitive these sensors are and the kind of data they provide on residual strain and impact energy, where does this go next? Could we see this technology evolving beyond just detecting damage that's already happened?
You mean like predicting the future?
Sort of. Could it potentially help us predict the remaining useful life of these composite structures based on the impacts they've sustained? It's definitely something to think about for the future of aerospace safety and maintenance.